Okay, welcome everyone to another talk in the Detector Virtual Workshop. Today's speaker is Dr. Bernard Rauscher. Bernie's an astrophysicist at NASA Goddard Space Flight Center. He's a civil servant. He works on the James Webb Space Telescope, where he's detector scientist, and the ISIM deputy project scientist. He's also principal investigator.
All these virtual people coming and going.
Spectrograph detector subsystem. Dr. Rauscher got his PhD from University of Chicago in the mid-90s. After that, he went to Durham and then on the Space Telescope Science Institute, where he and I worked together testing detectors for JWST.
Hey Don, how many people have you actually got there on site?
We have six. And
I can see my little talk bar talking.
Yeah. And then Bernie went to NASA Goddard. So now, Bernie, I'll give it over to you for your talk on the JWST near-infrared spectrograph detectors, and I'll go ahead and sign off on my video.
So can you hear me, Don? Okay, I will go ahead, and I need to share my screen, correct? So I share my desktop. This is not going to work, but we'll see.
How do we tell if it's working?
Don, am I broadcasting? Don? It's not working. Okay, Tom sees.
Can you hear?
Perfect. Okay, so I'll go back to full screen. Actually, I like the half screen because that way I can see. Okay, so Don, you've got my cell number there, right? Okay, we're going back to full screen then. I can't see those pop-up messages when I'm there. So what I'm going to be telling you today is about some work that we're doing that is aimed at reducing the noise of the James Webb Space Telescope near-infrared spectrograph detectors using what we call improved reference sampling and subtraction. I'm speaking on the part of a large team here at Goddard, some of the folks that you see listed there. And then there are many others as well who you'll see photos of a little bit further in the talk. So this chart basically is one that in the spirit of many a jazz musician I lifted from John Mather, and he borrowed it from Charlie Pellerin, and it comes from a great observatories brochure of the mid-1980s that was intended to convince Congress that HST, the Compton Gamma Ray Observatory, Chandra, and Spitzer were good things to do. And that effort worked because we built all four. And so here you see some of the great questions of the day that were being asked then. Some along the lines of how did the universe begin, and will we find the laws that govern inflation? We've made some progress on those with Kobe and MAP. Obviously a lot of work to go still on inflation. Then others are less well understood. For instance, we've learned quite a bit about how to assemble clumps of dark matter into structures that might evolve into galaxies, but we don't really have a good understanding about how to turn those clumps of dark matter into the galaxies that we see today and evolve them. We now know that black holes exist. On the other hand, there's much to know about how black holes come to be, how stars are born, and how they die, both of which take place in heavily obscured regions of the universe for which wavelengths that Hubble in particular is not ideally adapted to or needed. And then finally planets have of course become a very big focus of astrophysics in the years since the 1980s. So we've made some progress, we've made some outstanding progress, but the question is of course how to do an encore on that. And so the encore was basically contained in the decadal survey of 2000 and then reiterated in 2010 that in 2000 in particular, what you want is you want a large infrared optimized space telescope that is placed in an orbit that actually allows you to take care take advantage of the properties of the infrared sky. The burning questions that were identified then have to do with the nature of the first light. And in the context of JWST, first light really means the turning on. We've got these clumps of dark matter that have distributed themselves throughout the universe, presumably through a hierarchical clustering mechanism or some other model. We now need to light those up. So the first generations of stars will supernova in sub-galaxy-sized clumps and generate what we tend to call first light in JWST. The birth of stars and planetary system, the assembly of galaxies, how do you get from those small sub-galaxy-sized clumps that you see at first light to the galaxies that we see today? And then finally, we'd like to understand planetary systems and the origins of life. So these four themes were identified as far back as Alan Dressler's report in the 1990s, and today they form the core of the JWST design reference mission. And then just to take it a step further, in 2010 we just had another decadal survey. That decadal survey reiterated the importance of JWST to answering all of those questions. It also included a wide field infrared survey telescope, WFIRST, that will use the same detector technology. And then of course ESA, independently of NASA naturally, has rolled out on their own Euclid concept to study dark energy, which is also envisioned to use the same Hawaii 2RG detectors and sidecar ASICs that we're going to be talking about in this talk. And then on the ground, the H2RG is widely used at many ground-based observatories today. And so it's a sensor that's had a huge impact to astronomy. And what we're going to tell you today is how we believe it makes sense to use the reference information that's built into the Hawaii 2RG, specifically with the sidecar ASICs that Teledyne also tells, but much of what you'll hear about is also applicable to a ground-based controller so long as you operate the detectors in the right way. This picture is really just to put into perspective how big JWST will be compared to Hubble and Spitzer. It's also not just about size, it's about wavelength coverage. Hubble was primarily visible and near UV, although it did make, of course, some inroads into the infrared with the NICMOS and now the Wide Field 3. And then Spitzer is, of course, focused out in the infrared. So JWST spans the range from the visible into the near and mid-infrared, and it does so with a much larger mirror, as you see there, and in a cryogenic orbit. I should say in an L2 orbit with a cryogenic temperature observatory. This chart just shows you some of the people and organizations that are involved in JWST. And I should say, I'm going through these charts on JWST and WFIRST and whatnot to put this work into a broader context. In one or two charts, I am going to focus in on the detectors. But backing up to the mission, it's an international project. There you see it. NASA Goddard is the lead, but we have partnered with the European Space Agency, the Canadian Space Agency. It has a near-infrared camera, a near-infrared spectrograph, a mid-infrared instrument, and a fine guidance sensor. And all of these instruments, except for the mid-infrared instrument, use the Hawaii 2RG detector arrays and the sidecar ASICs that I'll be talking about today, although the specific software that I'm describing that lives in the sidecar is planned only for the near spec right now because that instrument is detector noise limited for most of what it does. So here's how JWST works. In the upper right, you see it packed into the Ariane 5 launch shroud. We launch it, and it will unfold into a structure like we have shown at the upper left. And then we send it out to an orbit out 1.5 kilometers beyond the moon in the Earth-Moon Lagrange L2 point. So, 0.5 gigameters, Dale says. So here we focus in a bit on the near spec, which is going to be focus of this talk. It is interesting to note that we have real hardware for all of these instruments that you see on the left there. Near spec is a multi-object spectrograph operating from 0.6 to 5 microns. We do that using a pair of identical Hawaii 2RG detector arrays with 5 micron cutoff material. In practice, Teledyne actually grows it a little bit longer than 5. I think it's 5.3 microns is the hard cutoff to ensure that we meet our QE spec at 5 microns. The field of view is 9.7 square arc minutes. has an integral field unit, has fixed slits as well as a micro shutter array that allows selecting up to 100 simultaneous targets and provides spectral resolutions of 100, 1000, and 3000. Now, near spec, shown at the upper right there at ESA's facility in Otterbrunn, I should say at Astrium's facility in Otterbrunn, Germany, is built to use the focal plane that you see at the upper left. That focal plane contains a pair of Teledyne H2RG detector arrays that look like that there, and a pair of sidecar ASICs that are packaged up to look like that there. And then this focal plane structure was designed by ITT Satellite Systems in Rochester, New York, the hardware that actually is containing these two components. The H2RG detector arrays you see right there, the photosensitive surface peeking through the shadow mask, and then the two sidecar ASICs are actually mounted immediately on the backside of the detector package. Now, for those who are not familiar with these near-infrared detector arrays, near-spec's H2RGs are hybrid sensors, and what that means is it's not a monolithic piece of silicon like a CCD. You build the detector material out of mercury cadmium telluride, which you see there. And then you build a separate readout integrated circuit, ROIC, and then you hybridize those two together with a sea of very small indium bumps and backfill that with an epoxy resin. JWST's detectors do have the epoxy backfill. I note that depending on the application, some people have the epoxy backfill or not in these hybrid detector arrays. Turning to the sidecar ASIC, that's basically an infrared array controller on a single microchip. It provides all of the biases, clocks, analog to digital conversion, along with a flexible CPU and memory in a small package. The package is about the size of a deck of cards, I guess one might say. And it's operated at the same temperature as the H2RG. Typically, well, at least for JWST, we've tried to keep them all within about 30 centimeters of the H2RG. So they're generally located very close to the H2RG and running at the same cryogenic temperatures as the H2RGs, which for near spec is going to be about 40 degrees Kelvin. The H2RG and the sidecar ASIC, the sidecar in particular, hugely simplifies the systems engineering for space applications because it's orders of magnitude lower mass and power consumption than a traditional implementation. And so it offers really outstanding performance when mass, power, and volume are paramount. And then on the lower left, you see a picture that I grabbed off the web of a leach controller in Don Feiger's lab. And then just roughly scaled to size is the sidecar ASIC to just try to put that comparison into perspective. Yeah, and Harvey also mentioned that the integration risk is reduced as well. So here's a snapshot of a few of the key requirements that folks can look at. Unlike a ground-based observatory, we do have the supremely low background that is afforded by the L2 orbit. So you see that 6 electrons in a 1,000-second noise spec, which one might think is very challenging for the detector. It turns out the H2RG can fairly easily meet that spec, we think. But when you integrate it into a full system like we have with the sidecars, you get the correlated noise that I'll be telling you about in a few minutes. Operating temperature is 40 K. Our mean dark current spec is 0.01 electrons per second per pixel. I will note that we routinely measure far lower than that. Our flight grade detectors come in at about 0.003, 0.004, something like that, and even that may be test set limited. We run them at a 100 kilohertz pixel rate, although the sidecars and H2RGs can run at a couple of times that. We run with 4 outputs per detector array. Both the pixel rate and the number of outputs are set primarily by the power dissipation requirements that we work to. The detector format is 2040 by 2040 photosensitive pixels, and that goes up to the 2048 to 2048 that some people may know when you include the reference pixels that frame the photosensitive image area. QE spec is 70 microns from 0.6 to 1 microns, 80% from 1 to 5 microns. And we have what on the surface of it appears to be a very low operability for science spec of 89%. But it's important to remember that that is at the end of the part's operational life. So they will have been on orbit for at least 5 years being irradiated for that entire time. So that 89% is intended to capture all of the degradation that will happen over the life of the parts, including a lifetime dose of radiation. Then on the right, you see just a very small number, really, of the people who were involved in all of this. Yi-Ting Wen there in the Dewar, you know, I think everybody did great work, but I would like to mention something about Yi-Ting in particular. We're getting outstanding noise performance out of the system, and that is what is actually allowing us to do this study. And so it is hugely gratifying as a science team to be able to work with folks like Yi-Ting and Brent and Greg Dello, Craig Cabelli out at Teledyne, Camden, and Ali, because they can deliver that kind of performance and allow us to focus on the kind of stuff I'm going to be talking about today. So much of what I'm going to be talking about concerns references. And a reference is any signal that mimics a normal pixel but does not respond to light. Just check, make sure. So the H2RG has been engineered to include both reference pixels and a reference output, and then depending on the instrument, and specifically near spec, because you'll recall on that FPA we had that opaque shadow mask blocking off the parts of the area that weren't being used, and we also have the micro shutter array being a spectrograph. There are other references that are available in the form of blanked off pixels, but here you see a little graphic of a near spec H2RG. And the different references that you have. You have 4 rows of reference pixels along what typically appears as the top and bottom of the image as an astronomer would see it in the orientation that Teledyne uses for their testing in their facility. You have 4 columns of reference pixels on the 2 sides. There's a separate reference output. So the H2RG has up to 32 video outputs looking at normal pixels, and then in addition there's another one which always looks at a specially engineered reference pixel. So there is this reference output that is always available. And then finally for near spec we do have these regular pixels that live behind the micro shutter array or that live behind the shadow mask, or if one wants to get sophisticated, which I'm sure we will, we'll take advantage of the blanked off shutters on either side of our targets and whatnot in the field. And apply the kind of formalism I'm going to show you today to try to derive a global correction using the real pixels as well as the reference pixels. So all of what I'm going to tell you about today builds on work by these folks. You have Mr. Gauss there in the lower left and Mr. Wiener in the upper right. Mr. Gauss was, of course, the pioneer of the least squares method, although I understand that Louis Laplace was also involved in developing that. And then you have Norbert Wiener, who applied all of this to signal theory and maybe more, but that's how he entered my world in terms of signal processing, like you'll see us talking about today. So our detector system is linear by design. And what we're after here is a way to apply the reference information that is optimal in a least squares sense. And that's a point where I'm hoping that Tom in particular will pick up on as we go through this, which is to say that throughout we're using frequentist statistics and a least squares formalism. And so we would really appreciate hearing about any ideas that anyone might have about other ways of approaching the statistical problem. We began all of this, however, with just characterizing the noise. And so what you see here is a noise power spectra using the traditional JWST readout, which I'll tell you in a minute. But basically, traditional JWST readout just sequentially cycles through the pixels at a steady cadence of 10 microseconds per pixel and builds up an integration like that, just maintaining a lockstep cadence of 100 kilohertz, looking at the pixels and then resetting every so often to delineate the exposures. But basically, we have the detector doing the same thing all the time insofar as is possible to maintain the power dissipation constant which is one of the tricks that was realized to be very powerful with these infrared detector arrays when they first became available in the mid-'80s, and has continued through to the current day. So on the left, you see the noise power spectrum on the conventional log-log plot, which reveals the 1/f noise quite nicely. And it also reveals a feature called the 300 hertz bump that, although it's not strictly speaking a part of the IRS squared, we have learned how to tune the ASIC, or more correctly, I should say that Marcus Luza has learned how to tune the ASIC to alter the shape of that 300 hertz bump and its detailed characteristics. Although I don't think he quite succeeded in getting rid of it completely. It is amenable to tuning, and we believe that it has to do with the drive strength of the circuit between the analog to digital converters and the preamps. On the right, what you see is the same thing, the Fourier noise power spectra, but this time on a linear semi-log scale. And what you see is the appearance of these high-frequency spikes in green. Those are something that we have learned how to largely tune out by adjusting. Once again, it's primarily drive strengths in the sidecar. These are, when you see a peak like this, it's telling you that one of the analog circuit elements is resonating. And so typically what we do is we adjust the drive strength to try to damp those down. And then finally, out at the Nyquist frequency, 50 kilohertz, you see this little uptick, and that manifests itself as an alternating column pattern. Big uptick, Harvey says, that manifests itself as alternating column noise. So armed with a large set of data, which primarily consisted of 100 dark ramps with 88 frames up the ramp, we did principal components analysis. Much of the material from this point onward is going to be quite detailed. I will say that Dale Fixon is working on a journal article, and there's also a pair of SPY papers that describe some of this that will give you all of the details. But to do the PCA, basically what you do is you very crudely fit, do a least squares fit of slopes to the up the ramp data, and then subtract out the dark current. So you now have the residuals around the fit, and you use those to construct a covariance matrix for the full data set. So we have 88 frames up the ramp per exposure, 100 exposures, so that gives us 8,800 frames of data that go into that covariance matrix. And then we typically prune the data in various ways to get it down to size and calculate the eigensystem. And once you have the eigensystem, the eigenvectors are the principal noise components. It's a linearly independent basis that you can use to operate on the noise without introducing any correlations. And then the eigenvalues give you the amplitudes of those different components. So when we did this, we found out quite convincingly that for frequencies faster than the frame rate, the noise is stationary, which basically means the covariance to a high degree of approximation, which means that the covariance matrix was diagonal to a high degree of approximation when viewed in Fourier space. Or to say it another way, what popped out of that calculating the eigensystem of the covariance matrix was that the eigenvectors were sines and cosines, and the eigenvalues had a 1/f spectrum. So that told us that the most natural basis was Fourier space, and when you go in and recompute the covariance matrix in Fourier space, lo and behold, it's quite diagonal, thus confirming that it was indeed stationary. We have learned in the last year that right around the frame rates of about 1/10 of a hertz, there are non-stationary components that become important, and we're still working to understand how to best deal with those. So what I'll be telling you about in today's talk is mostly done in Fourier space, operating optimally on the components that are stationary. And we may hopefully come back and tell you we've done a little bit better once we get the lowest frequencies fully under control. So here's how we do it and how it differs from the traditional readout. So to set the context, on the upper left, you see a schematic of a JWST Hawaii 2RG detector array. It's read out in 4 thick bands that are 512 pixels wide and 2048 pixels long. The fast scan directions are horizontal on this plot. The slow scan directions are vertical. And you just sequentially cycle through the pixels, working your way from the bottom to the top in this image. And Harvey was really one who first realized it, that when you do it this way, there are really too few reference pixels and they're just too far apart to actually get at all of the noise that we want to get at. So what we came up with is what is shown on the right, which we call improved reference sampling and subtraction, IRS squared. Here I've zoomed in on the lower left-hand corner of the detector. And what you see happening is that every so often, n over 2 pixels, where n stands for normal pixel, we step out to the reference pixels and we digitize r over 2 reference pixels, and then step over to the next reference pixel, digitize r over 2 of that, and then step back in and continue our cadence. To give you an example of what these numbers are, pretty typically we have 16 normal pixels for every 4 reference pixels is one of the more common readout modes that we've been using. And so the advantage of this is that you have many more reference pixels available in your frame, and you're sampling the reference pixels much more frequently. And so that is the key thing that we're doing differently in terms of taking the data. It doesn't require any hardware changes with the sidecar ASIC. What it does require is a knowledgeable sidecar programmer, and we had Marcus Luza do this for us. Although there's obviously no reason why somebody else couldn't do it as well, but it does constitute a bit of a programming job. I think it took Marcus about 3 or 4 weeks working part-time. Okay. Yeah, so it was on the order of a month or so, but Marcus was not working full-time on this before we were ready to go. Now what I'm going to show you is how all of this looks in the Fourier domain. So in addition to the improved reference sampling, we do the improved reference subtraction. And this is something that we took out of our first paper in 2010, and you can see the reference down there. Of the material that's currently in literature, that paper is probably the one that gives the best overview of what the theory is. There's another paper that I wrote, so Rauscher is the first author at the 2011 SPI in San Diego you can search for that will provide an update. Anyway, what you see here in looking at the upper right-hand corner is the ratio of the reference output, I should say, of the detector pixels to the reference pixels, the ratio of the amplitude of the ratio of the FFTs, if that makes sense, to the reference output. So this is the average value of the Fourier transform of the regular pixel stream divided by the reference pixel stream, both dealt with as complex quantities, and then we calculate the amplitude of that. And the important point in the upper right-hand pane is that, first off, for frequencies less than a few kilohertz, about 3 kilohertz, the gain is not 1. So there is actually a gain difference between the reference output and the regular pixels, and that gain is about 0.8. And over a couple of different H2RGs now, we've found that that's a robust conclusion. So typically we've been finding that there is this gain difference at low frequencies of about 0.8 times. And Harvey has commented that the gain is the relative amplitude of the correlated noise component. And then on the bottom pane, what you see is the phase, which is likewise important, and what we've been finding to be a fairly general conclusion so far is that the phase difference is essentially 0 while the noise is correlated. And then once you lose correlation, it of course becomes unconstrained. So what we're dealing with here between the regular pixels and the reference pixels, at least, is a frequency-dependent gain difference, or what this means in practice is that when one uses the reference output, one would need to, the way I tend to phrase it is you would need to apply a filter to it that corrects for this gain difference and rolls the frequencies off at about 3 kilohertz. And using the formulism you'll see in a few charts, you can actually learn how to actually compute the optimal Wiener filter for implementing that filtering. Surprised there are no questions. Don, I'm going to drop out for just a minute and make sure everything's still okay. So let's just see. Okay, so back we go. Okay, now here we see further detail on some of the measured weights. I will say that Rick Arendt did these beautiful FFTs. There's an awful lot of processing that goes into getting an FFT this clean, so people might want to speak to us if you find your FFTs aren't coming out quite this clean. But anyway, we have these beautifully clean FFTs, and there you see in more detail on the upper left the weights that should be applied to the reference output. This is for a different detector, so the spectral characteristics are a little different, but once again, you get about this factor of 0.8 in the gain. You also see the interleaved reference pixels there. I'm going to come back with a much better chart on that later, so we'll discuss the interleaved reference pixels later when we get to that better chart. On the right, you see a very important point, which is that the weight, once again, we're going to take care of that one again in a later chart. Here, the x-axis, we've actually shifted it so that the Nyquist frequency appears at 0. And so what you see on these particular charts is that the Nyquist frequency appears at 0 because we've done that shift. And you see that the 1/f noise has modulated the Nyquist frequency. And that is a signal that is picked up by the reference pixels and only the reference pixels. And I have another chart that will re-emphasize that point later. And that appears as odd, even alternating column noise for those of you who are working with these detectors. So for those who just can't wait to get with it, here are all of the equations on one page for how to do this. It's actually best to use both the reference pixels and the reference output and calculate these frequency-dependent weights. So I'm not going to go through this in any great detail, but what you see is the starting point is equation number 1, where we say that the reference corrected normal pixels is equal to the raw normal pixel stream, where you need to reformat all of these kinds of information into time-ordered vectors. You need to fill over all the gaps due to things like dead time between rows and dead time between frames. And you need to interpolate over all of the statistical outliers like cosmic ray hits to make sure you have nice, clean vectors, because we're going to be dealing with linear operations. So this equation treats the normal pixel stream n as a vector, the reference output stream, which is rho, as a vector, and the interleaved reference pixel stream also as a vector. And what we do is we use a large number of dark ramps to simultaneously fit for the frequency-dependent coefficients alpha of nu and beta of nu. And like I said, I'm not going to go through this in detail, but to do that, all you really need to do, just like in good old-fashioned least squares, is keep track of a couple of sums. Here they are. I will note that they're generally not real sums. They are complex quantities because you're working in Fourier space. So you do need to keep track of the complex quantities in doing all of that.
The top 3 are real.
Dale has pointed out that the top 3 are in fact real. The resolution I've got on my screen, I can barely read it. But the equations are there for those who want to try. And then in equation 11 and 12, you actually see the weights. And then finally, in the final equation, you see us applying the correction. And I will say, you can either do it using a Fourier paradigm, like is shown here, or you can do it by just convolving the relevant vector with a kernel that you derive by inverting the filter that you've applied. So the key point contained in equation 1 is it's a simple linear model. We start with an over-constrained system with lots and lots of dark ramps, and then simultaneously fit for the alpha of nu and beta of nu. And here's what I was getting at a few minutes ago when I said I had much better plots of what the coefficients looked like. Here we see an example of some real coefficients that are coming out of a near flight grade detector that we have in our Pathfinder here at Goddard. We only see the key bottom 2.5 kilohertz in this first pane, where blue is the interleaved reference pixels, red is the reference output, and then the light gray is the sum of the two, which is giving you an indication of the overall correlated component that's present. And the important point to note is that the reference output and the interleaved reference pixels do very different things in this paradigm. The red, the reference output, you'll notice becomes important at high frequencies, but takes very little of the weight at the lowest frequencies. And then the interleaved reference pixels in blue are what does most of the correction at the lowest frequencies that are present. And then these little ticks that you see in the data, the ticks down, the ticks up, that's the row rate of the H2RG. Now what I'm going to overlay is the full frequency range, which is of course 50 kilohertz with our 100 kilohertz pixel rate. And there is a filter that has been applied to the reference output, which is why it drops to 0 at about 3 kilohertz. And then for those with very good eyes, you'll notice a little bit of blue picking up again at the far right-hand corner, right at the Nyquist frequency. And that little bit of blue is the interleaved reference pixels picking up the alternating column fixed pattern noise. So that's a component that the reference output is powerless to track because we believe it's coming in the actual H2RG ROIC. There are even and odd bus drivers, and so it's a different set of drivers on those two buses. So you actually need the interleaved reference pixels, which see those different drivers, to pick up that alternating column component, which is significant. And it's particularly important for a spectrograph because alternating columns look an awful lot like alternating lines if one is so inclined. So here's what happens when you do all of that back in the time domain. So on the upper, on the figure on the right, the two left-hand panes are traditional readout. The upper left is a full field exposure of an engineering grade H2RG and an engineering grade sidecar ASIC. And what you see is faint horizontal banding. And I will say from having looked at a large number of these H2RG and sidecar systems over the years, it's not at all unusual to have some faint horizontal banding, which is the hallmark of the 1/F noise. And then on the bottom, we zoom in on a little postage stamp so you can get a better look at what the faint banding looks like. And then on the right, we have done the improved reference sampling subtraction IRS squared. And the immediate impression is that the variance is much lower. The banding is significantly reduced. And then if you look in the lower right, you see that it's a much cleaner image in terms of the correlated noise that you're left with. And this is actually, we believe, a very important advantage because when you're trying to detect faint sources and assess the statistical significance of sources, it's much easier to do once you've gotten the correlations out of your data. If you leave the correlations in, then you actually have to include all of those correlated off-diagonal terms in the covariance, and not everyone does that, and so one can be tripped up if you don't. So cleaner is better, and that's what you see. Here's the benefit viewed at the frame rate and higher in the Fourier domain, and once again you see very large improvements. There's a factor of 2 at the high frequencies. That comes about largely because in the traditional H2RG and sidecar implementation, the reference output is fed back to the differential inputs in the sidecar with unity gain. And so that opens up the bandwidth for everything from 3 kilohertz out to 50 kilohertz. And as you've already shown, that's uncorrelated. So you would expect a factor of 2 in the variance at high frequencies, and you get it because you're effectively cutting the bandwidth of the measurement almost in half. Then there's a factor of 80 near 20 hertz and 400 hertz, and once again a big factor 25 for less than 1 hertz. And then in the interest of full disclosure, this chart does cut off at 0.1 hertz, which is about the frame rate, and we are still working on understanding everything that's going on at the lower frequencies and the residual correlations down there. So once you've processed your data to get the correlated noise out in those in the time domain, at least within a frame, How you go about doing the up-the-ramp fitting is also important. What most people do, and certainly what we were doing in the lab here on JWST, is just a 2-parameter unweighted least squares fit. And that is a best linear unbiased estimator if all data points have equal uncertainty and the uncertainties are all uncorrelated. It turns out that both of these conditions are generally false, at least for our near-infrared detector data. So the good thing about the unweighted least squares is that it is indeed unbiased, so you won't get yourself into any trouble in terms of biasing your data, but it is not optimal. And so we found that you can actually do a few percent better if you do a generalized least squares, and so that's what's shown here, where you need to have some estimate of the covariance. And now the covariance I'm talking about is the covariance in those 65 samples up the ramp. It's not the covariance that we've been talking about up to this point, which is the covariance, strictly speaking, in the time domain. This is still in the time domain, but for JWST, the samples are 10.7 seconds apart, as opposed to 10 microseconds apart. So if you do that, you can improve things by a few percent. I will say that by eye, at least, the data do not appear to be terribly Gaussian, and so I've put a little picture of Thomas Bayes down there to see if I can inspire anybody who knows anything about different ways of doing the statistics to suggest a better way that we might do our up-the-ramp fitting, given that we do have correlated noise in there. For a fact, we know that we do have residual 1 over f, for instance. So we've got residual 1 over f, and we've certainly got shot noise from the photons in addition to the read noise that we need to deal with. We do have a robust formalism, of course, with the generalized least squares, but better is always better. This chart was supposed to be knocked out, and it wasn't, so we'll skip over it. So, and then more generally, Mr. Bayes is back. All of this has been what is called a frequentist approach, builds on Gauss. As Dale put early on, when we were toying with names and finally came up with IRS squared, which was, I think, suggested by Marcus, one of the ideas that Dale had was, well, what Gauss would have done. And I think it's an actual assessment because it builds so strongly on the least squares formalism. And it is optimal so long as the uncertainties are all Gauss normal. But that is quite debatable for our data. We don't know that it's false because we usually have to average across many pixels to actually get a statistically significant result. But it does open up the question of is optimal in a least square sense the global optimum or not? And so we'd certainly be interested in hearing about better ways to approach applying the references to use all of the information that's there. So here's one for the folks out there who might be involved in either building detectors themselves or in contracting with folks to build them better detectors. We've gotten to the point in this study now where I think we're starting to see the limitations in the H2RG. We're not yet there where we're cleanly H2RG limited. We'll know that we're done when we have nice diagonal covariance matrices and with all terms on the diagonal having equal amplitude. But we are starting to get to that. So if I were in a position right now to design new detector arrays or ASICs for astronomy, and I say this for low background astronomy where we do these long staring exposures, then there are a few simple things that I would aim to do, and I've put the actual hardware changes in blue. One, which is a piece of low-hanging fruit, is that the reference output is fantastic for reducing the noise within a frame. But its spectral characteristics, as you saw, are actually poorly matched to the regular pixels. The gain's not quite right at low frequencies, and there is no information content at frequencies higher than 3 kilohertz, at least for the ones that we've looked at. So in the ASIC package, at minimum, I would look at adding in the handful of passive components that are needed to match the spectral properties of the reference signal to the real pixels. And if this didn't turn out, one could always put shorting resistors on the pads. So the issue is really just engineering in some pads and the fan out for your sidecar. If one were actually re-engineering the sidecar, then we could have a discussion about actual changes in the sidecar layout. But that's usually a much bigger thing. Whereas this is something that you could sneak into the package, I think, and quickly gain some of what we're talking about. Then, right now, only the reference pixels that are built into each output see the noise that is specific to that output. And as Harvey said early on, there are too few of them and they're too far apart. So it would be really nice to have engineered in reference pixels that can be flexibly interleaved with the regular pixels without disturbing the clocking. The way that we've done it right now, we're using the guide window functionality to basically sit there and look at reference pixels. So for near spec, this is not a problem because we weren't planning to use that guide mode in general. We have some applications, but for a lot of things we didn't need it, so we can use it for the IRS squared. But for general observing, it would sure be nice to have a way to interleave the reference pixels and still keep your guide window. And then I would also ensure that the reference pixels that you do interleave are available on both the even and odd numbered column buses. And here, more general is better. You know, it would be nice to have be able to interleave as often as one reference per real pixel, or something less aggressive, just depending on the noise properties. Then there are some noise components, like the picture frame, that people who've worked with the H2RG before are probably familiar with. That appears to not be visible in the reference pixels that are engineered into the H2RG ROIC. So for that, it would be nice to have some reference pixels that actually terminate in the Mercad-Tel. And I would also be interested in, and this is really not a hardware change, but one of the things we are going to do for JWST is study reset scenarios that deliberately reset a grid of pixels, say, into hard saturation so they no longer respond to light. And then we can try to use those to track some of this stuff that only appears in the Mercad. And then at some point, and just with some crude filtering experiments I've done, I think we're starting to get close. The 1/f noise in the unit cell source followers is going to become dominant. We'll know we're there because the covariance matrices will be diagonal with equal variance. When we finally get there, it would sure be nice to have that be a nice low noise FET. And in particular, you want to engineer it for low 1/f. So as a preemptive strike, I say, and this is something you do only if it's fairly straightforward to do as part of an overall respin of the readout. I would put some attention on engineering that first FET to achieve lower 1/f. So in summary, we're working on a Wiener optimal approach to using the reference output and reference pixels that are built into the H2RG. The improved reference sampling and subtraction IRS squared, it's optimal in a least square sense, which of course begs the question of whether there are other senses that might be globally optimal with lower noise still. For applying the reference corrections, this is the calculating of those weights that you saw. For up the ramp fitting, and then even stacking the calibrated images. I didn't go into that in detail, but for JWST, we take large numbers of identical exposures. This is also how the Hubble deep fields and ultra deep fields are done. And then what you do is you average together the pixels in some way. And when I look at the histograms at the pixel level that go into that, you see that they are non-Gaussian. So it would be nice to have some formalism, something that's not ad hoc, for identifying when a particular pixel has valid data and should be included in an average or not. Right now, astronomers do that with a variety of tools like Gauss fitting and throw out everything that's a certain number of sigma out, or iterative sigma clipping where you calculate a standard deviation and throw out the points. What I'm saying here is something that's statistically more valid, like the Wiener optimal approach you've seen to applying the references that builds on the least squares formalism. Some statistical way of making an informed decision about whether a particular piece of data needs to be included or not, and how it should be weighted if it is included. Then, stepping up to the big question, the IRS squared noise reductions to date. These numbers here are with a near flight grade detector array. I didn't go into great detail about the engineering detector that we covered earlier, but with the flight grade, we start at 6.5 electrons, which is actually non-compliant with the instrument spec, which is 6 electrons. When we apply our IRS squared formalism, we drop that to 6.1. And then when we use real pixels that are guaranteed to live in the dark all the time, we can drop that to 5.5. I think we'll ultimately drop it a little bit lower still by applying the same kind of formalism that you saw today to this blanked off pixels. Right now we're just making a DC correction where in fact we should do the principal components analysis and probably fit the first few components and subtract those rather than just a DC correction. Now importantly though, the images that you get, as you saw earlier, are much cleaner with much less banding and much less visible correlated noise, which means that you can have much more confidence in the statistical conclusions that you infer from those data. I will say there are some hints that with the engineering grade hardware we got significantly better reduction, and I should say more than hints, we did get significantly better reduction, but we didn't focus on that hard enough that I would want to be putting up numbers. But we did see very large gains with engineering grade components. So that's another way one could look at this, is a way of improving yield, potentially improving the yield in your program by making parts that have a lot of 1/f noise be more suitable for flight. And then we're still working to understand some non-stationary noise at the very low frequencies, and hopefully we can come back and tell you about all of that once we have that understood and under control. So that is my talk, and I'm going to go over and turn the desktop over to Don. So Don, you should be back.
Can you hear me, Bernie?
Yes, we can.
Okay, let's thank Bernie. So Bernie, we have some questions that have accumulated up here in the chat window. So how about if we go ahead and start with the first one. Maybe you can see them there. It's from Tom Laredo asking, how heavily does this tax the sidecar CPU? That's the, I guess, the real-time implementation of this filter.
I'm looking at, I'm going to go up to it. Okay, so how heavily does this tax the sidecar CPU? Right now, well, we have Donna Wilson sitting here who actually did that work. Could you come around, Donna? Maybe you could say something about that.
Sure. As far as CPU utilization, we're within any flight margins that we...
To ask a question or chime in through audio, just let me know. I can give you a microphone.
She's here. You have to just get closer.
Oh, it's your computer. Okay. One of the changes that was made for this readout was that we went from the nominal full-frame microcontroller clock, which is 500 kilohertz. We increased it to be equivalent to the 10 megahertz clock that comes from externally from the sidecar on JWST. So we are running at the maximum possible CPU clock for JWST. However, the sidecar can run even more quickly than that if it had a faster external clock. For instance, on some other programs, the external clock was up to 30 megahertz. In addition to that, when you talk about sidecar CPU, a lot of the processing is done kind of at the ends of the frame, and then during the middle of the frame, while we're clocking off the detector, the microprocessor isn't so busy as much as the H clocks, which are auto-generated by a state machine, a separate pattern generator, and flowing the analogs through the digitization channel. So my summary of that is to say that I'm not really very worried about CPU utilization in this mode. We are still within any margins we need for flight.
Does that answer it?
Okay, so I guess the short answer is not a lot, right?
Acceptably. And we do have a very stringent power dissipation requirement. You know, somebody who's working on the ground, I think, could do quite a bit more with the CPU than we are.
So Tom was just asking down there at the bottom. He was wondering if there's enough headroom in processing power to do more stuff.
There is. The issue with us is that we have a power dissipation spec. That means that Dale is all full of clever ideas for how we would use that CPU if we had more power.
The problem is that we can't send them more data too.
Yeah, Harvey mentioned we have two constraints for JWST. One is we have a power dissipation constraint for near spec that's around about 17 milliwatts plus or minus a few. And then the other is we have a hard data volume constraint because the solid state recorder either already exists or is at least specified. So we're only allowed to save so much data. So I think the answer, Tom, for JWST, there is an array processor which is lower power that we can use for simple things like co-adding while sitting on a pixel. But the actual CPU, I don't think we're going to be able to do anything more with.
But that's not because of utilization.
That's right. Okay, that's it, Don.
Did you want to move on to Bill Forrest's question?
Okay, so Bill's question is how much of the correlator noise which R squared eliminates is attributable to the sidecar rather than the H2RG mux? The answer to that is right now an awful lot of it. I know that because when we take this detector that we get down to, the best that we've gotten out of this particular detector using the IRS squared in the sidecar is about 5.3 electrons RMS. I reported the 5.5 because it's a much larger data set and so statistically more valid, but I've gotten it down as low as 5.3. If we take that same detector and read it out with one of the detector characterization lab leach controllers here, this is something that E. Ting did, he's had it down as low as 4.7, 4.8 electrons under the same bias conditions. But that's comparing a single-ended readout of the H2RG with a controller that dissipates hundreds of watts to the sidecar, to the IRS squared running at about 17 milliwatts. But anyway, the point is I think an awful lot of it is coming from the sidecar.
Oh, Bernie, what's the gain setting of the sidecar?
Oh, well, the number I know offhand is we have it set so that it's 1.24 electrons per ADU. I don't recall offhand what the analog setting is.
Okay, that sounds like 8. Yeah. Oh, right. Okay. Let's see. The next question is, what's the physical cause of the ratio of amplitudes between the reference pixels and science pixels? You know, you said it was 0.8, and that kind of sounds like a FET.
Marcus has Marcus and Teledyne. You know, we've discussed this both with Marcus and the engineers at Teledyne, and all have assured us that it is exactly the same electronic circuit on that one.
Circuit, but FET may be bigger.
But it is a different FET. And so Harvey's pointing out is it may be a bigger FET, but it's not an extra FET. It's the same. It's the same schematic. It may just be a somewhat different FET.
Right. Right. Which could lead to the gain difference.
Yeah. But the key point is once you know it's there, it's actually an easy fix. The issue is if you don't, then you're just injecting noise when you use it.
The sensitivity to fluctuations on the source of drain voltages could depend on details of how they're biased as well.
That's right. Harvey was mentioning the sensitivity could also depend on the bias condition.
Okay, the next question here is, did you do an experiment to try out your idea of putting discrete capacitors or filters on the output of the reference outputs like you recommended for future design?
I haven't. I would like to try that. I think for W First, I've been coordinating with Ed Chang, who leads their focal plane engineering, to see if we can at least get the pads into their fan-out card for their sidecar. So I think that opportunity is likely to come up in the context of W First, but I haven't discussed it with Ed for a couple of weeks. It is something that would need to be done. Like I said, I was viewing it as the kind of thing where you engineer in the pads, and if it works, you're good to go. And if for some reason there's some subtle gotcha, you can always put in a shorting resistor with no loss.
Okay, Bill Forrest has another question. Are you detecting and eliminating RTS or popcorn noise?
Good question. I was just asking this the other day. We need to look over the data and see how much of that is in there. We haven't done it yet.
Okay, and I think there's, I have another question. Are any of these improvements being implemented into the H4RG?
I am working with Teledyne on various aspects of that. I would defer to Teledyne to say as much as or as little as they wish about their new products.
Okay, and then there's a final question from Kenny.
Yeah, there was also one from Tom, I think, about what up the ramp was.
Yeah, Don answered it.
You answered that, Don?
Sort of an inside. I think I answered it, unless Tom wants more
Okay.
information.
Okay, so Kenny's question. So it's how often will the IRS squared correction factors be updated during the mission as traps in the detector and ASIC change due to radiation damage? What we would do is we would simply add to those sums. There's that list of sums that's shown on the equation chart, and I would frankly simply add every dark that we get that passes some quality flag into those sums. There's no reason not to just update them continuously.
Sort of a rolling average.
Yeah.
Okay, those are.
Yeah, Harvey's point was you might want to do a rolling average actually if you find the parts are changing. Okay. Yes. Maybe I should try and put the chart back up. Give me a sec. I'm going to try and put the chart back up. And it's the one where the two are overlaid, right?
Yeah.
So here goes.
It's one of the very first ones.
Let's just see. You think it was 23?
Yes.
Okay, is this the chart?
No, the early one.
No, this is the chart? Okay. Okay. Let me blow it up to full screen then. Rick, I think you remember what those were? Was that due to how we were handling the interpolation? Yeah.
100 and 1,000 hertz, those are row frequency spikes, and it has to do with how you interpolate
That's
at
right.
the end of the row.
So between 100 and 1,000 hertz or so, those are spikes at the end of the rows. There are 12 pixels of overhead at the end of each row that we interpolate over using sines and cosines that we fit to the data. I'm not sure that was fully phased in when we did this, but even if it was, there were still going to be some relics. My recollection is there's about 1% of the variance that's contained in that fuzz.
Once it's corrected.
Once it's corrected, yeah. So overall, you win, even with that fuzz.
And what's very high frequency? Oh, there in the few kilohertz.
Those are those weird high frequency spikes.
Okay, we'll leave it at that. Okay. No, this has been very helpful, Don. I think this is a great little thing you've got going here. Yep.
Good.
Okay, well, thank you, Don. Thanks, everybody, and good luck, Don. This is, like I said, I think this is a nice little facility you got set up here.
Yeah.
Thank you. Bye.